So if you recall, last class you watched a little video that I recorded out in my backyard where my one daughter was standing in the center of a circle holding onto a rope, my other daughter was going around a circle at different speeds, different radii, and then at the end I picked up the rope and I was going around in a circle. And so I made up a little problem here for us to solve. Now, I don't want you to write down the problem, I just want you to read the problem, and we're going to talk through how we would solve this problem. Okay, so I made some estimations based on the video, what it took for me to complete this, and I want to figure out how much work Katie, my daughter, was doing on me as I was going in the circle. So let's just, again, I'm not going to write out the problem, let's just draw a picture of what was happening. We'll draw a top-down view. So let's say there's Katie in the center, there's her head, and this is my head. I'm going around in a circular fashion around Katie. And we'll just add some things to the picture. Of course, my motion had a tangential velocity, so there's my velocity vector. It always tangent to the circular path. And of course, we know anytime there's circular motion, which way does the net force point? Right, it has to point towards the center. That's that idea of centripetal force. So it's sigma F will point towards the center. And remember, sigma F and F sub c are literally just the same thing. Specifically, what kind of force was providing the centripetal force? Well, remember, there was a rope connecting me and Katie, and so it was a tension force that was pointing towards the center. But that's, of course, the same thing in this case as sigma F, because that was the only net external force. Now, I want to find how much work Katie was doing on me, and the work is being done by tension, a non-conservative force. So just, pause the video and think what equation we could use to find work. Well, hopefully remember that's going to be F delta x cosine theta. Okay, so we're not going to actually solve the problem. Again, we're just talking about how the problem will be done. Let's consider what would be put in here. So the force in this case, well, that's basically sigma F. In this case, that's the tension, right? And so the tension here I've estimated is 12.4 newtons. And then delta x, well, delta x is actually not displacement. Now, hopefully remember, when we're talking about a non-conservative force, really this isn't delta x. It really should be almost like d for distance. This is more like a path length. And you want to think about how many times they go around. And so we take the circumference of the circle, multiply by the 2.7 revolutions to get the total path length. That's what would go in there for delta x. But what about theta? Ooh, it's been a while, right? Let's remind ourselves, where is theta measured whenever we do this equation? Well, hopefully you remember, it's always the angle between the two previous vectors. In this case, it's the angle between the force and the motion. And so the force is pointing towards the center, the motion is pointing tangent. What angle is there? Well, hopefully you know that's going to be a 90-degree angle, right? Because the force is pointing radially inward, and the velocity vector, or the displacement vector, is pointing tangent to the circle. There's always going to be a 90-degree angle between them. And what's cosine 90? Of course, that's 0. So how much work was Katie doing? That's right, OJ. Okay, 0 joules, right? Now, if you remember watching the video, and if you don't, you can always go back and watch it again if you'd like to. It didn't look like Katie was doing no work on me, right? In fact, it looked like she was kind of struggling to keep me in the circle. And if we were to ask her, was it difficult to keep me in the circle? She'd say, of course it was. So it definitely required effort. So to get 0 joules of work, that's kind of insulting to her, right? There's no way she was doing 0 joules of work, and yet that's what the math is telling us, right? As long as the angle is always 90 degrees, cosine 90 is 0, and that's what it's saying. The work is 0 joules. Well, let's take this from another perspective. Again, we're finding the work done by sigma F, so this is basically like finding the net work. How do we know this is sigma F? Well, if we were to draw a free body diagram of me, we would certainly have weight, but remember, weight is sort of pointing into the screen because we're looking down at me. And then, of course, I was supported by the ground, so there's going to be a normal force, and the normal force is a bit kind of weird. It's pointing out of the screen towards you, right? And I was just going on level ground, so my weight and normal force were canceling each other out. And so really, the tension in the rope was the net force. And so this is also finding the net work. But you'll recall we have another equation for net work. Pause the video and think it through. It's a little equation, but it's a really, really important equation. I remember I called it the central equation of work and energy. Net work is, of course, equal to change in kinetic energy, right? And so we can say the net work is 0 joules because this is the work done by the net force, and that's saying that the change in kinetic energy is 0 joules. Well, how could that be? What does it mean to have the change in kinetic energy being equal to 0 joules? What's happening? Well, hopefully you said that if the change in kinetic energy is 0, there's no change in kinetic energy. Well, there's no change in mass. That means that there's no change in speed. hopefully you didn't say no change in velocity, because remember, of course, kinetic energy is a scalar quantity. Remember, we never talk about velocity with respect to kinetic energy, we talk about speed, and we know from circular motion that my velocity was always changing, right? I was going in a circle, so the direction was always changing, but remember, kinetic energy doesn't depend on that, it depends on speed. So as long as I maintain a constant speed, that means that my change in kinetic energy was zero, and that means that the network on me must have been zero. And yet, when you watch the video, it really looked like my daughter was struggling. So what does that mean? Well, the only way for this network to be zero is if the change in kinetic energy is zero, for me to be going at a constant speed. That's pretty unlikely, right? Humans are not really good at maintaining a constant speed, but we see that if I did maintain a constant speed, there really was no work necessary to keep me in that circle. From the other perspective, the network, or the work done by the tension force, had to be zero if theta is 90 degrees, which means that I'd be going in a perfect circle. And the only way for the net force to be pointing straight inwards and my velocity always be pointing tangent to the circle is if there's always a 90-degree angle between these two. That would mean I have to be going in a perfect circle. And again, humans are not really good at going in perfect circles. Because I was pulling on Katie and sort of moving her away from the center, she was kind of struggling to keep me in the circle, so she was moving around a bit. And so more than likely, I wasn't tracing out a perfect circle. I was probably going in some sort of weird elliptical path that constantly changed the shape, and so it's very unlikely that this angle was always 90 degrees. But if I could have maintained a perfect circular path, and so theta is always 90 degrees, and if I could have maintained a constant speed, so the change in kinetic energy is zero, then the network would definitely be zero, or the work done by the centripetal force would definitely be zero. So putting it all together, we can sort of summarize it by saying this. In uniform circular motion, the centripetal force does no work. It's pretty unlikely to have this in a real-world situation. It's sort of a contrived example, but there are some cases it could happen, and certainly some cases in nature where this can happen. So it's a good result to keep in mind.